Tutorial on complex numbers. This is the third video of full complex numbers for the Edexcel Further Pure 1 course. Now do bear in mind I've done a video in the FP1 playlist called the Factor Theorem. It's not technically an FP1 but it's required throughout this entire tutorial. So if you're not familiar with the Factor Theorem, go back one video, watch that before you even attempt anything here, because everything here requires the knowledge of the Factor Theorem. Okay, let's have a look at what Edexcel says we need to know. Everything in green is what I say we have done so far. We've talked about what complex numbers are, we've talked about real and imaginary parts, we've added, subtracted, multiplied and divided complex numbers, and we've even looked how complex numbers arose from quadratic equations, and that's where we're going to start actually this tutorial. But mainly we're going to focus on conjugate complex roots with real coefficients, and we're going to use the knowledge that if z1 is a root of a polynomial, then its complex conjugate is also a root. Right, let's begin by looking at how complex numbers arise. Here is a quadratic equation, and we want to know the solution for that quadratic equation. Now there are several ways of doing it. You could complete the square, or you could use the quadratic formula. You can't factorize in this case. Let's just for ease use the quadratic formula. A in this case is 1, B in this case is 6, and C in this case is 25. Now the quadratic formula tells us that x is equal to negative b plus and minus the square root of b squared minus 4ac, and all of that divided by 2a. Okay, then let's have a go at actually working out each of the x's. X is therefore negative b, which is negative 6, plus or minus the square root of 6 squared, which is b squared, which is 36, subtract 4 times 1 times 25, which would be subtract 100, and all of that would be divided by 2 times 1, which is 2, and x would therefore be equal to negative 6 plus or minus the square root of negative 64 all over 2, and you should know that the square root of negative 64 is 8i. Okay, so this is therefore equal to, x is equal to negative 6 plus or minus 8i over 2. And what you can do is you can divide both of these by 2, and we would have our answers. There are two answers. X on the one hand is negative 3 plus 4i, and x is equal to, on the other hand, negative 3 subtract 4i. And there are two answers. Now the reason I'm showing this example, you should all be able to do that from our previous work, but it's quite interesting. These two roots, they look very like each other, apart from this is a plus and this is a subtract. Now these are, from our previous work, these are complex conjugates, so both of these are complex conjugates. So the answer to this quadratic equation, there were two answers because it's quadratic, and they were complex conjugates, or they were conjugate pairs. And that's the idea we're going to use throughout this video. There's even a theorem for it, and I'm going to show you that theorem next slide. Now the theorem says the following. It's called the complex conjugate root theorem. If a complex number, a plus ib, is a root of a polynomial that has real coefficients, then its complex conjugate, z star, a minus ib, is also a root. So whenever a complex number is a root of a polynomial that has real coefficients, then its complex conjugate is also a root. And another way of saying that is when a polynomial with real number coefficients has complex roots, they occur in complex conjugate pairs. Now here, the coefficients are the number in front of the x squareds, the x's, etc. A is 1, B is 6, and C is 25. They're certainly real, and we just found out that the roots of that, well, one root we said was it was negative 3 plus 4i, and the other root we said is z star, is its complex conjugate, is negative 3, subtract 4i. And those two appeared in roots, in complex conjugate pairs. Now we're going to use this idea for higher order polynomials that are more complicated than x squareds, maybe x cubes, x to the power 4s, etc. Okay, let's do an example to develop this idea further. Here's example 2. It tells us, example 2, that 7 plus 2i is a root of a polynomial. I should actually write it's a quadratic polynomial. I should have written that to make it clear. A quadratic polynomial with real coefficients. Find the equation it is the root of, or find an equation it is the root of. Now, by the complex conjugate root theorem, you know that if 7 plus 2i is a root, then 7 minus 2i is a root, its complex conjugate. So you know the roots, you can state both roots of a quadratic is 7 plus 2i is one root, and 7 subtract 2i is the other root. Okay? So they're the roots of this particular polynomial. Now, if I know their roots, that's a root and that's a root, then for certain I know that x subtract the first root, which is 7 plus 2i, using the factor theorem here, x subtract 2i, that's a factor. And what's the other factor? Well, x subtract 7 minus 2i, the other root. They must be the two factors of this quadratic polynomial. Okay, so that's using the factor theorem. Look at the previous video if you're unclear there, but it works the same with complex roots as it did with real roots. That is a root, so x minus that is a factor. 7 minus 2i is a root, so x subtract 7 minus 2i is a factor. Now, we're trying to find the polynomial from which it came. If I just go ahead now and expand this, I will end up finding myself the polynomial that had those as the roots. Let's do it bit by bit. X times the x is x squared. X times the negative 7 minus 2i. Well, I'm just going to write that for now as minus x, 7 minus 2i. Okay? I'm going to write underneath, I'm going to keep writing this underneath. Now, I'm going to go for this negative 7 minus 2i times this x now. So that would give me a minus x 7 plus 2i. And lastly, I'm going to get this times this, which would give me a plus 7 minus 2i, 7 plus 2i. Okay? Now, let's try and tidy that up. Now, let's try and do it a little bit cleverly so we don't create too much work for ourselves. We still have an x squared. Now, this here is going to give me, this times this is going to give me a negative 7x. This times this is going to give me a negative 7x. In total, I'm going to have negative 14x. This times this is going to give me positive 2xi. This times this is going to give me negative 2xi. They cancel, so I don't get any more terms. And this times this here is the difference of two squares. 7 minus 2i over 7 plus 2i. Sorry, times 7 plus 2i. So it's going to work the way difference of two squares works. I would get 7 squared, and then I would get subtract 2i squared. Okay? And then what we're going to do, we are going to then combine everything. That's still x squared. That's 14x. And here, I'm going to get 7 squared, subtract 2i squared. Now, 2i squared, let me just write it up here. I don't want to, 2i squared is going to be 4i squared, 2i all squared, which is negative 4. So this here is negative 4. So 7 squared, subtract negative 4, would be 49, subtract negative 4, which would be positive 53. And here is your polynomial from which those roots came. So the equation that you solved to get those roots must have been x squared minus 14x plus 53, and that equals 0. That must have been the equation you solved to get these roots. Okay, I'm going to continue developing the idea. We're going to get harder and harder with the examples and let you have a go at a few at the end. The next one asks us to show that x is 2 is a root of this cubic equation, and it says using that knowledge factorize the expression completely and solve. Okay, you need to know your knowledge from the factor theorem video and the previous video. The first thing I'm going to do is call this polynomial f of x. I'm going to say f of x is equal to x cubed minus 6x squared plus 21x subtract 26. Now, by the factor theorem, if 2 is a root, okay, then I know f of 2, if I put 2 into this equation, I must get 0, okay, for 2 to be a root. So let's check that's true. 2 cubed is 8, subtract 6 times 4 is 24, add 21 times 2, which is 42, and then subtract 26. And indeed, that will give you the answer 0. So, because f of 2 is 0, then 2 is certainly a root. But moreover than that, because f of 2 is 0, you also know by the factor theorem that x minus 2 is a factor. 100% sure that x minus 2 is a factor. So we can write this expression down here. We can write down the thing we're trying to factorize, x cubed minus 6x squared plus 21x minus 26, okay? And we know that x minus 2 is one of the factors. And then we can use what we did in the previous video to find what needs to go in this bracket to multiply by the x minus 2 to give me the thing we're trying to factorize. What needs going here to multiply by the x to give me the x cubed? Well, x squared, certainly. And that would give me the x cubed I'm after, but it would create for me negative 2x squared. I don't want negative 2x squared, I want negative 6x squared. So I'm going to need another negative 4x squared. What needs going here to multiply by the x to give me the negative 4x squared? Well, surely negative 4x. And that gives me the negative 4x squared I'm after, but it creates for me positive 8x. Now I don't want positive 8x, okay? I want positive 21x. So I'm going to have to add in 13x. What needs going here to multiply by this x to give me the 13x? Well, 13 must go there. And that times that does give me the positive 13x I'm after, and it creates for me the negative 26, which is what I was after. So I have factorized this. Okay, now we are going to, that is factorized here. Can I factorize this further? I can't factorize that further because I can't think of two numbers that multiply to 13 and add to negative 4, because 13 is a prime number. So what I can do here, that's fully factorized. That's one factor, that's the other factor. Okay? Now, I'm going to just rub out this work in here. Okay? Now, that's as far as I can go in terms of factorizing, and I'm trying to solve this polynomial of 0. So what I'm trying to solve x minus 2, x squared minus 4x plus 13, and that is 0. So, I have two brackets multiplying to give 0. Either this is 0, in which case x is 2, or this thing's 0. So x squared minus 4x plus 13 is 0. Okay, now at this stage, I need to find the x's that make this equal to 0. Now, I don't want to, in this video, go through all of this, but this here is simply a case of substituting into the quadratic formula where a is 1, b is negative 4, and c is equal to 13. If you substitute those into the quadratic formula, you keep your x's 2 as one answer, and your other answers will be in complex conjugates. They will be complex conjugates of each other, and they will be one of the x's will be 2 plus 3i, and the other of the x's will be obviously 2 subtract 3i. And they would be your three answers. Now getting from here to here is not hard, it's just a case of substituting into the quadratic formula and checking you can get these. But I don't want to go through that in this video. So we've used the factor theorem there, we factorised a cubic, and we then used the quadratic formula to get solutions to that cubic. So I factorised and completely solved. Okay, building up with another example. Here's another example, again slightly harder. Example 4. It is given that -1 is a root of this equation. Find k. Well, first of all, I always like calling my polynomial something, so I always like calling it f of x. So I'm going to write it down. F of x is equal to x cubed minus x squared plus 3x plus k. Now, I know that -1 is a root. So I know that if I substitute -1 into this equation, I must get the answer 0. So let's sub in -1 cubed to -1, subtract -1 squared is 1, plus 3 times -1, which would be -3, plus k. Now I know this by the factor theorem must be 0. Because when I put -1 into the polynomial, because -1's a root, it makes the polynomial equal to 0. Now let's collect this up. That's telling me that -5 plus k is therefore 0, and it tells me therefore that k must have the value of 5 if I add 5 to both sides. Now, it asks you then, we've done part A, so this is part A nicely done. It asks you to find the two other roots of the equation. It asks you to find the two other roots of the equation. So let's do what we did previously. We know k now, so we can write this as a full cubic. So I'm trying to factorise x cubed minus x squared plus 3x, okay, plus 5. And I've been told that -1 is a root. So x plus 1 must be a factor. Now let's do what we did before to get what should be in this other bracket. What needs going here to multiply by x to get x cubed? Well, x squared, surely. And then I'll get my x cubed and I'm done. It creates for me a positive x squared. So it creates for me a positive x squared. I don't want positive x squared. I want negative x squared. So I'm going to have to subtract a negative 2x squared here. What needs going here to multiply by the x to give me the negative 2x squared? Negative 2x. And that gives me that is what I'm after. But it also creates for me a negative 2x times 1 and negative 2x. I don't want negative 2x. I want positive 3x. So I'm going to have to add 5x to fix it. What needs going here to multiply by the x to give me that 5x? Well, 5. And I'm done then, because that 5 times that 1 gives me the 5 I'm after, and everything's in order. Now, can I factorise this further? Two numbers that multiply to 5 add to -2? No, because 5's prime. So, what am I trying to solve now? I'm going to rub all this bit of working out here. What I'm trying to solve, if I'm trying to solve this is equal to 0, it's equivalent to solving the factorised version, x plus 1, x squared minus 2x plus 5 equals 0. Now, I've got two brackets equals 0. Either that's 0, in which case x is -1, or this whole thing's 0. Or x squared minus 2x plus 5 equals 0. Now, to solve that, I would encourage you to use the quadratic formula again, where a is 1, b is -2, and c is equal to 5. And if you do that, you will find yourself some complex answers. So you will find two answers that are complex conjugates of each other. I'm not going to go through plugging that into the quadratic formula. You should be able to do that yourself. And so x is equal to 1 plus 2i, and x on the other hand must be the complex conjugate of that 1 subtract 2i. So the three answers were x is -1, and the other two roots that they asked for in the question were this one here and this one here. And we're done. Right, let's move on to example 5. Starting to get really complicated here and get, this is called a quartic. The highest power is a power of 4. Now, this is going to be quite tricky. It tells us that 3 plus I is a root of this equation. And it says, hence you can solve the equation completely. Now, the first thing to note is to use the complex conjugate root theorem. I know 3 plus I is a root. And because I know roots occur in complex conjugates, I also know that 3 minus I is a root. Okay? And going further with the factor theorem, I know the following. I also know that a factor of this must be x minus 3 plus I. Because 3 plus I is a root, x minus 3 plus I is a factor, and the other factor is x minus 3 minus I. I know they are two of the factors of this. Now there are other factors, but I'm not going to worry too much about them. First, they're the two factors. And let me just multiply these factors out here to get what polynomial. This would give me some quadratic here that would help me later factorize this. So I'm going to try and expand this out. X times x is x squared. X times negative 3 minus I is negative x 3 minus I. Negative 3 plus I times x gives me negative x 3 plus I. And negative 3 plus I times negative 3 plus I, well, that gives me a plus 3 plus I 3 minus I. Now we've seen one a bit like this before. Let's just try and do it quite sensibly. I keep my x squared. Negative 3x I'm going to get from here, and another negative 3x, which gives me negative 6x, plus xi minus xi cancels, and this is the difference of two squares, and it's going to be 9 plus 1. If you multiply that out, it's going to be 3 squared plus 1 squared, so it's going to be plus 10. Okay, so two of the factors multiply out to this. So if I'm trying to factorize this thing here, I can write this on the left hand side like I usually do. Okay, and I know these two are factors, so this here is a factor. The multiplied out version of these two together is a factor. So I know x squared minus 6x plus 10 is a factor. Now the question is here, can I work out what must be over here to multiply by this to give me that? Well, I can. I can do it the way I've been doing it, but it's just a little bit more complex, a little bit bigger. It's going to take me a bit more working than I've got space for here. So if I just highlight this and bring it onto another page, that will help me to show you more clearly how it works. So I'm just going to group this together, and I'm going to copy this and add it to another page, and we're going to try and work out what needs to be in this bracket here. Now, the question we're going to ask ourselves, I want 2x to the power of 4. I want that here. What needs to go here to multiply by the x squared to give me 2x to the power of 4? Well, 2x squared must do. And that gives me the 2x to the power of 4, but actually creates for me a negative 12x cubed. So it creates for me a negative 12x cubed, and it creates for me also a plus 20x squared. Okay? Now, I'm going to deal with this column first. Let's fix this. I don't want negative 12x cubed. I want negative 3x cubed. So I'm going to have to add on 9x cubed. What needs to go here so that when I multiply it by the x squared, I get 9x cubed? Well, plus 9x. Now, that fixes me up here and gives me the 9x cubed I'm looking for, but creates for me a negative 54x, so I'll use a different colour, creates for me a negative 54x squared, and it also creates for me a plus 90x. Okay? Now, currently, I've created for myself a negative 34x squared, these two combined. I don't want negative 34x squared. I want negative 39x squared. So I'm going to have to subtract another 5x squared. What needs to go here to multiply by this to give me the negative 5x squared? Well, negative 5 does. That gives me everything I need in that column to add up to negative 39x squared. It also creates for me a plus 30x. That's what I wanted, because the 90 and the 30 give me the 120 I'm after. And it creates for me a negative 50 as well. And that shows I've done it right. I have now factorized these totally correctly. So, what went in the other bracket from this working? 2x squared plus 9x minus 5. So in this other bracket must go 2x squared plus 9x minus 5. Okay, and now it's just a case of solving the equation completely. I know that and that as a root. The other roots I'm going to get from this over here. Now, this actually factorizes nicely for me as 2x minus 1, x plus 5. I know the solutions of this thing here. The solutions of this here are given to me in the question. It's 3 plus I and 3 minus I. So the only other solutions I need here are when that's 0 and when that's 0, i.e. x is a half and x is minus 5. So my answers for x in this case are going to be 3 plus I is complex conjugate, 3 subtract I. When this is 0, I get it's a half, and when this is 0, it's negative 5. Now that is a very complicated question there, a lot of involved work. So go through it a couple of times if need be, but hopefully you found that quite helpful. I'm going to do one more example, example 6, again with a quartic. This is really good practice with your algebra, so hopefully we can do this. And then at the end I'm going to ask you to try some yourself. Right, let's give the last example a go. You need to show that x squared plus 4 is a factor of this. And then what you need to do is therefore solve this quartic. To show this is a factor, I'm going to do what I've been doing on the previous slides. I'm trying to factorize this, so I'm trying to factorize x to the 4 minus 2x cubed plus 21x squared, subtract 8x plus 68. Okay? And if it's a factor, I'm going to be able to factorize it out, as so. Okay? Now the question is, what needs to go in this bracket to make it all work? Well, let's give it a go. What needs to go here to multiply by x squared to give me x4? Well, x squared does. And it gives me the x4 I'm after. But it creates for me a 4x squared. Okay, so it creates for me a 4x squared as well. Now, the next thing I need to do, I fixed this column. I want to fix how many cubes I've got before I worry about this. So what needs to go here? I've got no x cubed currently. I want 2x cubes. What needs to go here to multiply by x squared to give me that? Well, minus 2x. And that gives me the negative 2x cubed. But it creates for me a negative, at the same time, it creates for me a negative 8x. As so. Okay, next column I want to fix is the x squared column. Okay, now I want to fix this column. I've got 4x squareds, I want 21x squareds. I'm going to have to add another 17x squareds to fix them to get 21x squared. What needs going here? So I multiply by the x squared to get me 17x squareds. Well, plus 17. That gives me the 17x squared, and that plus the 4x squared gives me 21x squared. But it also creates for me a plus 68. Now we had the minus 8x in the right column, that's done, and now we've got the 68 in the right column, and so we're done. So that is the proper factorization of this. Okay, now I want to solve this is equal 0. Okay, so I want to solve now this here is equal to 0 because it says next part, hence solve this equation. Okay, so what are we going to get as our answers? Well, on the one hand, this bracket is 0. So on the one hand, x squared plus 4 is 0. So x squared must be equal to negative 4. So taking square roots of both sides, x must be equal to plus or minus 2i. Okay? And there's one set of solutions. On the other hand, x squared minus 2x plus 17, well, that must be equal to 0. And I encourage you to use the quadratic formula where a is 1, b is negative 2, and c is 17 to work out what the answers are for those. And the answers for those are x is 1 plus 4i and x is 1 minus 4i. And hence we have our four answers. So x is, I might write that out as 2. X is on the one hand 2i, or x is negative 2i, or x is 1 plus 4i, or x is 1 minus 4i. And we're finally at last done. So these are really complicated questions. I hope you followed them. Take some detailed notes. Make sure you understand. I've got a few questions for you to do at the end. Dip into these, see what ones you can do, and I'll put the answers at the end. I'm not going through these. These are for you to go through yourself and check you can get. Here we go. In 10 seconds I'll show you the answer. So pause the video if you want to have a go at some. And the answers are as follows. And then just to finish, I would suggest looking in your FP1 book, reading chapter 1, page 24 to 29, and doing exercise 1H. And then tune in to the last video on complex numbers. Thank you for watching.